We often treat our 5G networks as the pinnacle of speed, but the sheer volume of our daily data usage is actually pushing current infrastructure toward a hard physical limit. From high-resolution streaming to massive cloud-based workflows, our modern habits require a continuous exponential increase in bandwidth that current standards were not designed to sustain. To increase data transmission speeds, engineers have to push signals to higher frequencies. Currently, this process relies on the electronic components found in our standard 5G towers. However, there is a technical roadblock at the 350 GHz threshold. Once a signal crosses that line, traditional electronic circuits struggle to process the information effectively. This chart illustrates the problem. As frequencies climb past 350 GHz, the signal encounters phase noise, digital distortion that turns a clean transmission into a chaotic scribble. This noise completely scrambles the data, making it effectively useless for communication. This means we cannot achieve 6G speeds simply by building better antennas. Reaching that next level of performance requires moving away from traditional electronic circuitry altogether. To find a solution, researchers at Tokushima University in Japan, led by Professor Takeshi Yasui, changed the fundamental approach to data transmission. They bypassed the limitations of electronics by switching the medium from electricity to photonics, using light to carry the signal instead of traditional electrical pulses. The core of their system is a device known as an optical microcomb, which replaces the role of conventional electronic circuits. Think of the optical microcomb as a high-precision laser ruler. It creates perfectly stable, parallel beams of light with almost no digital noise. This maintains a clean data stream at 560 GHz, far beyond where traditional electronics fail. While lasers are powerful, they are typically too fragile for daily use. Even a microscopic vibration can knock the components out of alignment and break the connection. The engineering breakthrough here was a method of permanently fusing an optical fiber directly onto a silicon nitride microresonator chip. This process condensed a massive, sensitive laboratory setup into a single, durable component. It is designed to be vibration-proof and includes internal temperature controls to ensure the lasers remain aligned in various environments. By shrinking this technology onto a chip, the team moved 6G from a theoretical laboratory experiment into a practical device capable of operating in the real world. In testing, this Japanese prototype achieved a consistent wireless transmission speed of 112 gigabits per second. This chart helps put that number in perspective. Compared to the highest speeds available on current 5G networks, this 6G prototype is more than 20 times faster. At this scale, the time required to download 4K movies or massive software updates drops from minutes to a fraction of a second. Because the bandwidth is so wide, streaming latency is effectively removed. This allows mobile devices to interact with remote cloud servers with zero perceptible delay. This responsiveness makes remote data processing feel as fast as a phone's own internal hardware, allowing for seamless use of cloud-based applications that previously required a wired connection. By shifting signal generation from electrical pulses to beams of light, this team has demonstrated a viable path to 112 gigabit speeds. In Japan, the physical mechanism for the next generation of wireless internet is now functioning on a single silicon chip.
Every new smart device and high-definition stream adds another layer of traffic to an invisible highway that is quickly reaching its limit. While 5G was built to handle this surge, current network usage is already pushing the standard toward its absolute physical ceiling. The problem lies in the hardware. Our networks rely on electronic circuits that push physical electrons to carry information, and there is only so much data these particles can move per second. As our digital demands grow, we are outscaling the physical capabilities of electron-based transmission, requiring a shift in the medium we use to send data. In wireless networking, speed is tied to frequency. To get more bandwidth, engineers have to transmit data on higher and higher frequency bands. But there is a wall. Traditional electronic circuits begin to fail when they are pushed past the 350 GHz threshold. Watch what happens when a signal crosses that line. The wave is hit by phase noise, extreme digital static causing chaotic interference. At these frequencies, data packets fragment and disappear, making standard electronics useless for ultra-high-speed networking. This isn't a simple design flaw. It is a limitation of how electrons behave in standard circuits at high speeds. To reach the speeds promised by 6G, we have to move beyond electrons and find a medium that can stay stable at much higher frequencies. Professor Takeshi Yasui and his team at Japan's Tokushima University have found that medium, successfully testing the world's first 6G prototype device. This chart shows the leap in performance. The prototype reached 112 gigabits per second on a 560 gigahertz band, a 20-fold increase over the peak capacity of 5G. They solved the noise problem by replacing electronic circuits with photonics, using pure light to carry the data instead of electrons. The breakthrough relies on an optical microcomb. Acting like a high-tech laser ruler, it produces highly precise, unwavering beams of light. This incredible stability reduces phase noise to near zero, allowing data to travel at 560 gigahertz without the interference that destroys electronic signals. By utilizing the stability of light, the team proved that terahertz data speeds are physically possible and scalable. However, high-end laser systems are usually massive and delicate. In typical labs, even a slight vibration can knock lasers out of alignment, breaking the connection. For 6G to work in the real world, this technology has to be small enough for a smartphone and tough enough to handle everyday movement. The Japanese team achieved this with a silicon nitride microresonator chip. They shrunk the entire system, fusing optical fibers directly to the silicon surface. By permanently bonding the fibers to the chip, they eliminated the risk of misalignment. The light path remains fixed, even if the device is moving or vibrating. The chip also includes dedicated temperature controls, ensuring the light frequency stays stable regardless of external heat or weather changes. This engineering takes 6G from a fragile laboratory experiment and turns it into a robust chip ready for consumer devices. A 20 times increase in bandwidth changes how we interact with the web on a daily basis. Massive file downloads that currently take minutes would be finished in seconds, effectively removing the wait times associated with high-capacity data. For real-time applications like virtual reality, this throughput allows for an uninterrupted flow of data. It minimizes the lag that currently causes stutters, making digital environments feel as responsive as the physical world. It also provides the capacity for dozens of smart devices to communicate across a single home network simultaneously, without any of them competing for bandwidth. By moving past the limitations of electrons and utilizing the stability of light, this tiny chip provides the infrastructure needed to support the next generation of digital innovation.